7 times 4. This simple computational problem came up when I was an undergraduate, and my instructor, Dave Coffey, talked about a scenario that has stuck with me to this day. Imagine a student who hasn't memorized this, they don't know this yet. They have access to a calculator, and they could do 7 times 4 normally and just kind of compute the answer, which is fine, a good way of getting the answer. But the scenario that Professor Coffey mentioned was, imagine you just tell the student, how would you compute 7 times 4 if the multiplication key was broken on your calculator? The times key just does not work, but you still have a calculator. What would you do to find 7 times 4? And, this leads to some interesting things where students can talk about, oh, I might do 7 plus 7 plus 7 plus 7. I use the plus key instead of the multiplication key, which shows a good connection between multiplication and addition. Or maybe they would think, oh, I can do 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. And they're switching it around to kind of working with the 4 and not needing actually the 7 key or the multiplication key. And so you can just start to think about, oh, what are some flexible ways of using this calculator and getting to the product without actually just directly computing the product? To me, this was kind of an exciting thing to think about because it took a simple problem and it opened up lots of opportunities for thinking and finding flexible paths to the answer and then comparing those and making connections. Much more richness than just doing 7 times 4 and getting the answer. So what I want to do in this video is talk about this technique, which can be generalized, and I call it the Roadblock Technique. And this is a technique that can be used to turn simple computational things or simple procedural exercises and turn them into more interesting problem-solving opportunities, into real problems. The Roadblock Technique, I call it that because you basically take a procedure that the students are very familiar with or comfortable with, and you throw a roadblock right in front of them. And they have to find a way to go around the roadblock. That's where the fun comes in. So I basically just want to share a few more examples of this, and then you can take it and run with it and generalize it to your own situations in your own curriculum. But with that 7 times 4, there's more than one roadblock you can do. You can throw in the roadblock of saying the multiplication key doesn't work. You could also throw in a different roadblock and say the 4 key doesn't work. And then you can look to see if students realize, oh, I can do 7 times 2 times 2. And that's a nice way of kind of breaking down the 4 into the product of 2 times 2. Avoid the 4 key that way. Or they might break it up a different way. They might say, oh, I'll do 7 times 3, and then I'll add on another 7. So I can get to the answer, but I didn't have to use the 4 key. But that one now I've kind of broken up the 4 additively into a 3 and a 1, and then used kind of, implicit distributive property to get there. Let's go to some sort of more algebraic examples. Say you had this equation that you're trying to solve, 2x minus 7 equals negative 4x plus 23, or whatever it might be. A lot of students might just feel like they have to start by combining like terms, like get the x's together, combine them, get the numbers together, combine those, the constants. But what if you threw in a roadblock and said, all right, solve this problem, but you can't combine like terms. You are not allowed to put them together. Even if they're a like term, we'll just play this little game and roadblock where we can't put them together. Can the students still figure it out? Well, they can still use a lot of flexible thinking. For example, you could still move the 2x and the 4x over to the same side of the equation so that you sort of have them together. And then you can have the 7 and the 23 on the other side of the equation. But I can't combine these. I now have to just sort of think about them. And what might you do just to think about them, reason about them? You might just break this down into x plus x plus x plus x plus x plus x and sort of just realize, oh, I've got a bunch of singular x's here, and it has to equal 30. So how can I break up that 30 into a similar number of chunks? I'd have to have some sort of a 6 instances of something that adds up to be 30, so that must be 5. And so then you kind of reason to the fact that x must be 5. Also going back up, if I had the 2x plus 4x equals 7 plus 23, I also might just notice some structure here that I have a 2x, and then I'm adding on double that. So I have kind of 2x plus its double. How can I write 30 so that it's a number plus its double? And that would be 10 plus 20. Now we can sort of see correspondingly that 2x is 10, and then 4x is 20, which means, oh, the x must be 5. But there's other ways too, just basically this kind of fun problem solving of how can I still reason to the solution, but not do my typical first step of combining like terms. Let's go forward a bit in the curriculum and look at some systems of equations. Say, for example, you had 6 plus y equals 2x, and then 2x minus 1 equals 3y plus 1, or whatever. You're solving a system of equations like this. And then let's say we can throw in a roadblock, which is that you cannot solve for a variable. You can't solve for y, or you can't solve for x. A lot of students will start to just get in that procedure of, I always want to solve for a variable first, and then I'll do substitution or whatever I want to do from there. But let's say you cannot solve for a variable. You have to just work with what you have here. Then let's get creative a little bit. You might notice some things, like you might notice, like, okay, if I'm not going to solve for a variable, I'm just going to look at what I have. I see that I actually have 2x equals 6 plus y, and the 2x shows up in the second equation. So I can actually just substitute like this. I don't need to solve for a variable and then substitute. I can just substitute the 6 plus y in for the 2x. And now I can go ahead and work on that one just in terms of y. A student also might just think about, oh, if I can't solve for a variable, then that sort of makes maybe the graphing technique hard, maybe it makes the substitution technique hard, but I still could do a combination technique, or what some people call elimination. So I might rearrange them in whatever way I want so that I could eliminate some things. Like maybe I'll move the 6 over, so I have a 2x minus 6 and a 2x minus 1, and those might eliminate nicely, and I can go from there. This roadblock technique can also be used in geometry or trigonometry or other things. It's basically whenever you have a kind of repetitive procedure or a certain strategy for solving an exercise that is a very common way of doing it, you can just ask yourself, what's a roadblock that I can throw in there, and then see if students can find their way around it. I'll give one more example maybe in trig. So if you have some right triangles that you're doing in trig, the sort of typical right triangle version of trig instead of the sort of covariational version of trig, but right triangle version is very common. And say we have a lot of these triangles and we're trying to find, the missing side or find the missing angle. You could have a worksheet like this, and you could throw in a roadblock and just say like, hey, try to solve these, but you're not allowed to use sine. See if you can solve all of them with cosine or tangent or other strategies. Sometimes they might really feel like sine is the one that fits the best, but they can be flexible enough to use cosine or tangent or other ways to get at the solution. So in general, I just like this roadblock technique because it's very flexible and a teacher can use it on the fly. You can just be in the moment and see an exercise happening or a certain single way of doing something, and then you can just say like, all right, I'm going to just throw in a roadblock and let the students work, and then it becomes kind of a problem that the students have to problem solve. So I think it's a way that in the moment or as you're planning lessons, you can create opportunities for problem solving even when the curriculum tends to be full of repetitive exercises. And I also think that using this roadblocks, it kind of can just change the message about what mathematics is. A lot of times mathematics is seen as sort of doing things the right way or the way that the teacher showed me. There's a single correct way that I'm supposed to solve problems. And then getting good at mathematics or being successful in mathematics is seen as I follow what the teacher said and I can do it exactly the way that the teacher said every time. This roadblock technique can really bust that open, and it can really say like, no, in mathematics there's lots of ways to think about these problems to get to the solutions. And in fact, that's one of the powerful things about mathematics, is that it's so robust and it all makes so much sense that you can get there in lots of ways. It's not so narrow and fragile that there's only one way to do something. That's a very weak sort of discipline. But no, mathematics is actually a much more robust discipline than that. And it can also include more students to say like, hey, let's look at other ways of doing this instead of just the way that I've kind of handed down from on high. So I think it can not only increase the opportunities for problem solving, but can also just increase the richness and robustness of what it even means to be doing mathematics together.